No, no. Okay. Okay, so Richard, you are muted. So okay, so next speaker is Professor Richard Woodard. He's going to tell us about the case for non-local modification of the gravity. Now you are in Taiwan. Okay, please start. Richard.
Okay, thank you. Let me join everyone else in thanking the organizers for setting up this fine conference and inviting me to speak to it. I think it is really very important to have in-depth discussions on these issues because I don't think we'll get anywhere at all by just talking past each other. It's a great pleasure to be here in Taiwan, speaking to you all. Taiwan is one of the few countries that doesn't have any local community spread of the coronavirus. And in consequence, it's very, very difficult to get to Taiwan. I know this because I was kept apart by the cruel pandemic for 6 months this year from my wife, who's a professor at this university. I was finally, with her efforts and mine, able to acquire this card, which is an alien resident card and permits me to be with my wife. And it only just came through last Friday, and I'm very happy to be here to address you all. So I'm going to tell you about, I'm not going to try and solve the ultraviolet problem. I wish I knew the answer to it, but rather than lying to you, I'm just going to talk about something else. I'm going to talk about the case for making non-local modifications of gravity. The case is pretty easy to make. The case for modifying gravity is pretty easy to make, and that is that it needs far too much dark stuff. It's embarrassing when you talk to people in the general public, when you show them this pie chart here, about how little we know about the universe and say, okay, well, the part that we've seen in the lab that you guys have paid, given us all this money for is less than 5%. And there's all this other stuff that we can detect gravitationally, but no other way. You all know that there are three sort of anomalies. First, we need dark matter to bind together cosmic structures, galaxies and galactic clusters. We need dark energy, the bigger amount of dark stuff, in order to drive cosmic acceleration. And we need that both now during primordial inflation. You can do it. You definitely. So if I think here I'm speaking to people who are pretty sympathetic to gravitational modifications. I quite often speak to people who are more establishment oriented, and they are just emphatic that there is no possible solution other than dark matter, and it's this particle or that particle. And if you just give us another $1 billion, we'll see it in this detector. They so far have come up empty. I'm not going to say that that you won't ever see it. You definitely can make it work, but it's a little bit epicyclic, and so far they haven't. So far we haven't seen the stuff, and so the only way that we've detected all this dark stuff is by violations of Einstein's equation being set equal to, or the Einstein tensor being set equal to the matter that we know, this embarrassing little less than 5%. That for sure doesn't work. That's what we detect. And what you then do to deal with this problem is you either modify the left-hand side of the equation or the right-hand side of the equation. The establishment is absolutely emphatic that we have to modify the right-hand side of the equation, add all this dark stuff, and that'll solve it. But it's at least worth examining whether or not we can solve the problem, one of the three problems, by modifying the left-hand side of the equation. And there are different choices that you get to make about doing this. They basically devolve to two beginning questions. First, do you want to employ additional fields to do it? And if you opt to employ additional fields, a prime example of that is Bekenstein's tensor vector scalar model. But then, you have to ask the question whether adding all these additional fields that sort of lock up part of the gravitational force that's missing, whether or not that's not just some recycled version of dark matter and dark energy. Another issue is, or you can employ only the metric. There, you're initially confronted with a very depressing no-go theorem, and that is that the only local, invariant, stable, metric-based theory is modifying the Einstein-Hilbert Lagrangian, which of course is r times the square root of minus g, to some function of r times the square root of minus g. And although that, for sure, Starobinsky taught us that that can give primordial inflation, it can't explain the current phase of dark energy, and it can't explain what's going on with dark matter. Or you can retain, so basically you have to abandon one of those three things, locality, invariance, or stability. I'm pretty firm against abandoning stability. So I know that there are a lot of people here who are very sympathetic towards abandoning stability, but I think the fact that the universe has been around almost 14 billion years is pretty strong evidence against doing that. So the choice really then devolves between abandoning locality or abandoning invariance. We've just heard a very nice talk by Andre about abandoning invariance, which I think is one of the few really viable options, that examples of that would be Harava gravity or massive gravity. There is, as we all know, a major problem to that, and that is that we have direct evidence now about the speed of gravitational radiation. It's very nearly c, so you have to somehow recover Lorentz invariance. Again, I'm not going to cast aspersions on anyone's work. I wouldn't say that you can't do it, but we all agree that that's an issue. Or you can retain invariance and abandon locality. That's what I'm going to talk about. I sense, that I'm in the dwindling cohort of Anglo-Saxon physicists on this planet. We Anglo-Saxons have to stick up for each other. So it behooves me to remind everybody about our great Anglo-Saxon predecessor's comment on non-locality. He, in his letter to Bentley, he denounced it as, quote, so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. Well, I wouldn't quite put it in those emphatic terms, but I basically agree with that statement. I know that there are others here who don't agree with that and think that fundamental non-locality is no big deal at all. Non-local theories, I think everybody is going to agree, will certainly have extra initial value data, as Irina mentioned to us. I believe that that is going to involve Ostrogradskian instabilities, and that's probably something to be avoided. Contrary statements typically make use of Euclidean momentum space. Of course, we live in Minkowski signature, so you have to somehow get back. The instability precludes doing a temporal Fourier transform, and if you just do the Euclidean K-space, you're assuming the result. The whole instability is that the theory tends to develop a very weird time evolution, and you're just not precluding that if you assume that you can do the temporal Fourier transform. So I'm going to avoid that and not advocate fundamental non-locality. I think that the fundamental theory is local, and actually I think it's Einstein's theory. But I do quantum gravity, and I know, as everyone else does, that quantum effective field equations are not local. Even at one loop order, you can see non-locality, important non-locality. And in fact, at one loop order in gravity, the non-local terms are much stronger at low energies and also at high energies than the local terms. It's for sure true that loops of massless quanta can give big infrared effects. And remember, the kinds of problems that I'm trying to explain are large-scale problems. So we are looking at what's going on in the infrared. And let's all take note of the fact that gravitons are massless. Now, whenever I propose that, I'm immediately shouted down by people who say, no, you can't ever have macroscopic quantum effects, we only see quantum effects at small distances. And that is true in earthbound laboratories. At least we only recognize quantum effects at small distances at low energies. But I would argue that it's easy to cook up field theories and adjust parameters in such a way that you could see them. And I'll just give you a simple example that I think everybody's familiar with, involving flat electromagnetism. So no gravity at all, just flat space electromagnetism with vacuum polarization at one loop order. And let's look at what happens to the electrodynamic response to a point charge. So you can see my point charge over here. What I've written is Coulomb's equation. The potential is capital phi of R. And the classical term is the minus del squared phi. The contribution to vacuum polarization is this term, which I've written as an integral over the norm of the Fourier momentum. And it has some factors that just come from doing the angular integrations times the electric susceptibility, which is what you get from doing a quantum field theory calculation. And I think everybody's done this calculation at one loop in quantum electrodynamics. The regulated result with a momentum cutoff capital lambda looks like this. And the counter term is delta chi sub E. And let's now examine this both when the electron mass is non-zero and when the electron mass is zero. When the electron mass is non-zero, we renormalize this to make the quantum correction vanish at k equals 0. That is, at large distances, the thing that we call the classical charge is, in fact, the thing that you would measure to be the classical charge. And that gives, after we make that choice for renormalization, that fixes this constant and cancels all the divergent lambdas and some of those. And we wind up with this well-known result for the electric susceptibility due to one-loop quantum electrodynamic vacuum polarization. It's too hard to solve that exactly, but it's easy to solve for what happens at small r. And the result is well known to be going like logarithm of 1 over m sub e times r. That's the well-known running of the electrodynamic coupling constant, and it's telling you that the electrodynamic coupling constant, the vacuum polarization, makes the electrodynamic coupling constant strong at short distances. Of course, it's getting so strong that it's non-perturbatively big, and two-loop results would become important, and you can't necessarily trust it, but the general tendency is there that it's getting strong. It's also not terrifically interesting because we're talking about the focus for my particular purpose, because I want to look at large distance effects rather than small distance effects. So let's remember small distance effects come from massless quanta that go around in loops. So this thing is coming from a diagram where a fermion is going around in a loop. So I want to make the fermion massless. Now, again, as soon as I do that, people will give me all these statements. No, the S matrix doesn't exist. You're right. I'm not saying otherwise. But this one equation, the quantum corrected effective Coulomb equation, still makes perfect sense. You can see it. You don't have to take my word for it. Look at it. It still makes perfect sense. The 1 over m whole here, when m sub e goes to 0, is exactly canceled by that. So it still makes perfect sense. But it changes how we can do renormalization. We can no longer make this renormalize in such a way that the quantum correction vanishes at k equals 0. Well, that's something we've encountered before. My good friend Bob Holdham would no doubt point out at this point that that's exactly the same thing that occurs in quantum chromodynamics. And what we do there is we just pick out a particular scale and we cause the quantum correction to vanish at that scale. And then there are positive corrections for scales that are smaller and negative corrections for scales that are bigger. And so if I call that scale k is equal to 1 over r, where r is some length, then the one loop renormalized vacuum polarization with 0 electron mass looks like that. And now I actually can solve it. This is simple enough that I can solve it exactly up to constant terms and it takes the form here. Now you can see that I've still got the behavior that we had near r equals 0, so that's still present, that didn't go away, and that still tells you that you can't trust perturbation theory. However, near r goes to infinity, where this particular form would have broken down, this form is now generally valid, still completely valid near r goes to infinity, and it tells you you've got 1 minus something. Okay, so now let's just appeal to the renormalization group, which tells you how to scale up or scale down distances. It's always valid. It's not always useful. It's only useful when the tendency of the flow is to cause the coupling constants to become smaller. So near capital R goes to 0, it's not going to be useful, or near little r goes to 0, it's not going to be useful, but near little r goes to infinity, where we're causing the coupling to become small, it is useful, and it can be used to completely resum the result. And so the result for the renormalization group corrected Coulomb potential takes this form. It's the classical result divided by this, and it just tells you that vacuum polarization at large distances causes the measured charge to go to 0. Well, that's, I think everybody understands physically why that's happening, because it costs no energy at all to create these electron-positron pairs, and their polarization, as you get larger and larger distance, builds up and eventually just cancels, completely screens the charge. And that's an example of macroscopic quantum field theory effect that we can get without even doing any sort of complicated physics. I'm of course not trying to sell you anything about quantum electrodynamics. We all know that the electron mass is not equal to 0. And I'm trying to tell you instead about quantum gravity. So what kind of things would drive quantum gravitational effects? Well, I think the thing that is driving them is the inflationary production of scalars and gravitons. Remember, to go back to the quantum electrodynamic result, the thing that's driving the effective charge down to 0 at large distances is the fact that it doesn't cost very much, it costs almost nothing, to create a massless pair of electron-positrons and the virtual particles that are associated with that induce a huge polarization that wipes out the bare charge. So what you need is to have a lot of virtual particles around, and we all know something which does that. Inflation produces a huge ensemble, vast beyond imagining, of scalars and gravitons, and it produces them at cosmological scales. Some people get upset about de Sitter results. So let me characterize the occupation number of these things for any cosmological geometry in terms of the measured scalar power spectrum, and I hope soon to be measured tensor power spectrum. So what the result is, if you just calculate the, this is trivial quantum field theory. You just linearize the theory, so you're looking at quadratic part of the energy of the quadratic part of the action, say. That is then mode by mode a harmonic oscillator. Just treat it as a harmonic oscillator and look in co-moving time, and then set the energy equal to h bar times the appropriate omega times n, some n plus a half. The n that you get is a measure of how occupied the state is. And for inflationary scalars, that goes like the measured power spectrum over these parameters times the first slow roll parameter times the scale factor squared. Notice this is happening for one wave vector. And of course, there's many, many, many wave vectors. For gravitons, the result is even simpler. It looks like the so far unmeasured, but I hope soon to be measured resolved tensor power spectrum. And again, this factor of a squared, which is growing like a bat out of hell during inflation. So there are vast beyond imagining number of infrared quanta around to do something. I regard it as self-evident that these particles must interact both with themselves and other quanta. It astounds me how many people are just emphatic in rejecting that. I'll comment on that, but let's talk about some of these effects. So I actually have been doing calculations with various collaborators, one of whom at least is present here among the attendees, my good friend and colleague, Tomislav Prokopets. And we have studied, he and I, with some other people, have studied quantum electrodynamics, scalar quantum, or actually E&M plus gravity on de Sitter background. And one of the things that you can see is that if you calculate the one loop correction to the vacuum polarization, you get that the field strength, the electric field strength of a dynamical photon picks up a logarithmic enhancement. It's down by a very small parameter, GH squared, which even during primordial inflation is a small number, less than 10 to the minus 10, but times a factor of the logarithm of the scale factor, which is just growing like the number of inflationary E-foldings. And depending upon how long inflation grows, that could be arbitrarily big. Another result, let's see, I think this was derived with, in that particular paper with my graduate student, Chenglong Wang. Another result that Tomislav and I got was that the Coulomb potential, along with Shunpei Miao and Dražen Glavin, is that the Coulomb potential, that is the response to a point charge, capital Q, goes like the classical result, the flat space result, just de Sitterized, where everywhere you had an R, you multiply it by the scale factor times R. Scale factor scales up distances, coordinate distances to make them physical. There is a effect that has been known since the earliest days of looking at quantum gravitational corrections to the potential. I think it was first resolved by a student of Schwinger. Let's see, the man's name slips my mind. I'm sorry about that. The fact that it's present even in the de Sitter result is a good correspondence check. And then you get the intrinsically de Sitter effect, which looks like, again, the same loop counting parameter, GH squared, times logarithm of the scale factor times H times the distance. So, in fact, this is growing both at late times and at large distances at fixed time. You can also look at what happens to gravity on de Sitter background. And you can do the same things. You can look at what happens to dynamical gravitons. They get a de Sitter, they get a D enhancement, so their amplitudes go down by, again, the same factor. And you can look at what happens to the potential, whereas this calculation was done from using a 1996 calculation that Nick Samus and I did of the graviton self-energy. And so this represents the gravitational contribution to the effect. This particular result was done using using a calculation that So-Yeon Park did for her thesis, giving the contribution to the graviton self-energy from massless minimally coupled scalars. And this particular result was derived with So-Yeon Park and Tomislav. We get, again, the usual de Sitterized version of the flat space result, a de Sitterized version of the well-known correction, one-loop correction in flat space that would only be big at very short distances, at Planck scale distance, and then these two big infrared effects, which are characterized by the same loop counting parameter and have a secular contribution and a contribution that's growing like large R. And interesting thing about these things is that these quantum corrections break down at large radius and at large time. So they become non-perturbatively strong. They're suppressed by a small loop counting parameter, but they get arbitrarily big if you wait long enough, or if you don't want to wait that long, if you insist, no, inflation is only 60 E-foldings, I'm not going to allow it to go longer than that. Okay, fine. How far is spatial distance? This term and that term will still get arbitrarily big. So somehow loop effects are getting to be big. And again, that's not some strange thing. That's just exactly what you would expect when you have massless particles running around in loops. You can probably sense my frustration because I do these calculations and they're not easy to do. They take about a year's time to do one of these calculations and to fully renormalize it and calculate exactly what's going on. And it is just infuriating to listen to collections of people who've never calculated any of these things and wouldn't even know how to calculate it, and dismiss it and just say that this is all ridiculous nonsense. I call these people the head in the sand faction because they seem to be just determined to argue that there is nothing going on. See, it seems to me that the reasonable approach for somebody who's not maybe an expert in this is to say, okay, there's obviously something going on. There's obviously an effect. Maybe it's big, maybe it's not big, maybe it grows non-perturbatively strong. We could all argue about that. But to say that it's zero, which is the establishment position, that's just lunatic madness. Nonetheless, that is very, very common, and I hear it all the time. Let me go over the four arguments that are sometimes made against this. The first one, which is I think the most serious one, is that the effects are gauge dependent. We're talking about quantum gravitational contributions where gravitons are really going around in loops, that can and does depend upon the choice of the graviton gauge, that's a totally valid objection. I would point out that that's not valid. Let's see here. For this last result that I mentioned, the one that Tomislav and I got using Soyun Park's, with Soyun, using Soyun Park's thesis calculation, that's massless minimally coupled scalars going around in loops. And for those who are gravity experts, you know that at one loop order, matter contributions to the graviton's self-energy are completely gauge independent. There's no gravitational loops. That's a completely gauge independent result. So that objection is just false for that particular objection. It seems to, and then in order to believe what my critics argue, that the effect is actually zero, you have to believe that, well, it can occur for a massless minimally coupled scalar, and the same kinds of things seem to occur in gravity, but it's all just zero, nothing happens, it's mathematically zero. That, I think, strains credulity to believe that. Further, there are clear flat space antecedents of this. Argue that gravitational, what's happening, the thing that's driving these effects, it's just that there's lots of gravitons being created during inflation, and those things are going to affect the kinematics of photons that try and move through it, other gravitons and things. To argue that that's not going to be true, well, let me put it in a positive. If you critics have a really good argument against that, you need to go tell the pulsar timing people who are spending on the order of $1 billion trying to create big radio telescopes and analyze carefully pulsar timing data. You need to tell them that the passage of a gravitational wave through past a photon that's propagating to us is just going to have zero effect, that you've proven it mathematically, because they don't believe it, and they've spent a lot of money doing it, and I personally believe that they will detect that effect pretty soon. Another argument made against
Richard,
it,
sorry.
Sure.
2 minutes are left. Please remember.
Okay. So
okay, sorry.
I'll speed up. There are some other arguments made against this. Let me just comment a little bit more about the gauge-dependent effect. Like I say, I think that argument is a real argument, and you do have to deal with it. And we are trying very hard to deal with it using technology that was invented by John Donahue in effective field theory. We've come up with a way of correcting the effective field equations so that you can take the gauge-dependent graviton self-energy and actually add in extra pieces to it to cancel the gauge dependence. And this table here, in terms of the two flat space Poincare invariant gauge fixing parameters A and B, is an example of how that works in flat space. And we're trying very hard to do that in de Sitter. And I think later this year we will have a result for it. Let me just finish up. I actually don't have very many more slides to do. Nonetheless, I still don't have any derivation of these effects. What I've shown you, I hope, is that the effects get non-perturbatively strong. To see what happens, you have to do some kind of a non-perturbative resummation. I don't have that non-perturbative resummation yet. So far, the models that I've been building are purely phenomenological, and it's a major problem then to connect them with these explicit perturbative calculations. Three kinds of things have been done. Non-local inflation models have been studied with myself and Nick Samus. Non-local cosmology models to try and explain the current phase of cosmological acceleration have been studied with Stanley Deser, and non-local realizations of Milgram's Mond model have been studied with Cédric Defayette and Gilles Esposito-Fariz to try and explain dark matter. These things are only phenomenological, and we haven't derived them. But just positing that they come from an inflationary origin gives you two things that are, I think, very important. First, there is an initial time so that you can use that to, and an initial value surface so that you can use that to define operators like 1 over the D'Alembertian. And that corresponds to essentially when the quantum field theory state was released. And second, you should expect modifications on large scales, not on small scales, because inflation is producing infrared scale gravitons. I don't have time to go through all three of these models. I picked out one particular one of them, the non-local Mond model that Cédric and Gilles and I created. The Lagrangian looks like this. So it's general relativity plus this correction where this thing Z of capital G is a non-local functional of the metric based on the inverse covariant scalar D'Alembertian acting on this combination of terms, which basically picks out the 0,0 component of the Ricci scalar, or the Ricci tensor rather. And that does the job. If you're looking at Mond, then you want to look in the weak field, the ultra weak field limit at the edge of a galaxy. In terms of the small perturbations around flat space, you can call the two potentials little b and little a. And what this Z thing degenerates for that is into b prime squared over a squared. And then if you take f of z to have this form 1/2 z minus 1/6 z to the 3/2, the z term cancels the general relativity term. The z to the 3/2 term gives rise to the Mond correction, which is necessary to give the Tully-Fisher correction, Tully-Fisher result. We've studied cosmology. These kinds of models don't have good, completely acceptable results in cosmology yet. So I'm out of time. Let me just give you my conclusions. So first, general relativity needs lots of dark stuff on cosmic scales. I am absolutely not telling you that has to have gravitational origin. The establishment believes, I wish I could ever be as convinced of something as the establishment people seem to be. They believe firmly that it has to be dark matter and dark energy. Maybe it is, I don't know, but it's at least worth examining the possibility that it's something else. The only stable local metric based modification of gravity that you can do is taking R going to F of R. Alexei taught us how that can give inflation, but it won't give dark matter, and it won't give late time acceleration. Non-local gravity is a new frontier where we can try and create models, so far purely phenomenological models, to try and replace this. And I think it's at least interesting to do. I'm not talking about making fundamental modifications of gravity that are non-local. I think that these things can and should derive from summing quantum gravitational corrections that have got non-perturbatively strong during inflation. So I think that this is coming from an effective field theory, examples of that is that it's vacuum polarization from inflationary gravitons. And if you just adopt that precept, even without a full derivation, then you already get two important things. First, there is an initial time, a good initial value surface that you can use to define things, non-local constructions that you would have, which otherwise you would not be able to define very well. And secondly, you should expect modifications at large scales, not at small scales. That isn't some fishy, funny thing that you put in. That's exactly what you would expect from this idea that it's coming from primordial inflation. Challenges are, of course, to derive it from first principles. I think that's not at all hopeless. Alexei again taught us how to sum up all the factors of logarithm of A that come from scalar potential models. It can't quite be as simple doing that using his technique to do that for gravity, but I think a combination of his technique and the renormalization group actually will allow us to sum them up for gravity. You need, of course, to have a model that avoids instabilities and is consistent with the results that we have about the speed of gravitational radiation being right, and you need to get structure formation right. So at that point, I'll sign off, or I'll end.
Thank you very much, Richard, for your nice talk. And there are a lot of interesting discussions on macroscopic quantum effect, but please discuss this issue in discussion session. So, Philip, please ask a question to Richard.
Richard, good afternoon or good evening. I think it's good night to you.
Yes, it's almost 9 o'clock here, 9 p.m.
First of all, well done on getting your
Go DM.
Yes, having the card is, I think, one wonderful thing for you.
Thank you. I'm so happy.
Yes, I share most of your reticence about the standard wisdom, except I reached a different conclusion. But I just wanted to say about your talk. You did this de Sitter correction to the electron, and you said, well, people object to it because inflation is no longer happening. But I think you would get a similar result if you did it in a Robertson-Walker metric with an A of t growing like t to the 2/3. It would just be a harder correct calculation, but I don't think you could possibly get 0. So,
I don't think anybody is objecting to it because inflation's no longer happening.
Okay.
They object from arguments that they say that in the prehistory of quantum field theory, there was a time before renormalization was understood when people could do loop corrections and they got divergences. Serious physicists took that seriously and tried to understand what was going on. The sort of head in the sands faction people just dismissed it and said, well, it's divergent, it must be 0. In the same sense, people say there is absolutely no question that a calculation of gravitational corrections to vacuum polarization or to the graviton self-energy, and indeed anything that involves a graviton propagator propagating around it, is going to be gauge dependent. No question at all, and I don't dispute that. I do dispute the conclusion that therefore the result is just 0. That I think is
absolutely
kind of a silly belief.
The other thing I wanted to comment on is about large-scale quantum effects. Well, we do have two. First of all, there's the stability of a white dwarf, which is due to the Pauli principle, and the cosmic microwave background is a black body. And that's quantum mechanics on the largest possible scale.
Oh, I absolutely would agree. They're both tree order effects, but I absolutely would agree. This is distinguished in the sense that it's a loop, a quantum loop effect, but I absolutely agree. There are, for sure, large-scale quantum effects.
Yes. So if we already see them in tree approximation, you shouldn't object if you see them in loops as well. I agree.
Look, I'm not going to dispute that. I'm totally happy with that conclusion. I think some of my critics would be happy seeing, some of my critics believe that they deserve the Nobel Prize for cosmological perturbations, and the tree order contribution to the cosmological perturbations, and that then thereafter there's zero, mathematically 0 correction to it. That I think is, so I really do need to make the argument about loop corrections, but look, you're right.
Okay, Alexei, please.
Okay, I have two small. Richard, happy to meet you here. After your that very interesting talk, I have only two small comments. The first, it's possible to construct models of present dark energy in F over R gravity, and actually a number of people, including myself, we constructed viable models. Unfortunately, I should honestly say that from the aesthetic point of view, they are not so elegant as the R plus R squared inflationary models. They require, I would say, rather anesthetic structure of a function f.
You're right, Alexei. I should have clarified something. What I was quoting is Dunsby's theorem, the theorem of Dunsby et al., that you can't get a stable de Sitter solution. But you're absolutely right. If you're happy, I mean, we don't know exactly that dark energy is the Sitter equation of state. And if you're happy getting it just close, phenomenologically close, that is within observational constraints to the de Sitter equation of state, then you're absolutely right.
Once more, it's possible in principle. And second, the comment, of course, where exists with infrared growth of gravitons in the process of inflation, and actually the only reason why we are more concentrated on scalar perturbations is simply because in slow roll inflationary models, graviton perturbations are suppressed compared to scalar ones. So we are more interested
by factors of the slow roll parameter, right?
Yes, exactly.
Or sure, no question about it.
Yes, but this effect also certainly exists, and actually, I would say that though it is not strictly shown, I would say that its classical limit is well known. It's a statement. If you consider a classical Einstein gravity plus cosmological constant, where asymptotic lake time behavior is not exact de Sitter at all. It's actually only locally de Sitter, but it can have arbitrary spatial dependence outside where the event horizon. And here we have complete the inverse analogy with what happens in general relativity. In general relativity, we have no hair theorem outside black holes, but not any such theorem inside black holes. So it's just the opposite. In the case of Einstein gravity with a cosmological constant, we may say that we have no hair de Sitter inside the Hubble the event horizon, but really has.
Perhaps you could share you could email me those papers. They sound very interesting. I'd love to look at them.
It's my old paper in 1983, which was developed in many papers after it. Okay, I shall send you the exact.
Thank you.
Reference.
Okay, so some questions are asked in chat, but time is almost running. So shall we move on to the next talk? Richard, thank you very much.
Yeah, I've stopped sharing.
Yes. Okay, so Ilya, please share your slide. Oh, great. Thanks.